In Chapter 16, we're going to cover the basics of confidence intervals. So what we're going to cover is the reasoning of statistical estimation, like why do we need to use a statistical estimate? How do we know how we can be confident in that estimate? The margin of error and confidence level. You may have seen margin of error in the news when they're saying like, oh, the president has a 40% approval rating within 2 percentage points. The 2 percentage points is the margin of error. Confidence intervals for a population mean, and how confidence intervals behave. So, first off, when it comes to statistical inference, after we've selected a sample from our population, we can learn the responses from the individuals in the sample, right? We're calculating a sample statistic. However, the reason for taking the sample is to use that sample statistic to make inference from that data about the wider population. So we take a sample, we collect its data. If it's a good sample, we use it to infer something about our population. Statistical inference provides methods for drawing conclusions about a population from a sample and that sample's data. So we have some simple conditions for inferences about a mean. And what this chapter will do is it'll present like the basics, but we're going to start with a setting that's like too simple to be realistic, but it's a good place to kind of get like our gut feeling for inference. So simple conditions for inferences about a mean. First, we have to have a simple random sample from our population, and there's no non-response or other practical difficulty, like there's no confounding variables, right? Our population is large compared to the size of the sample. The variable we measure has to have an exactly normal distribution, with mu being the mean of our population and sigma being our population standard deviation. And we don't know the population mean, but we know the population standard deviation. And that sounds counterintuitive, but these are like our very like simple idea, i.e. too simple to be realistic. Note, the conditions that we have a perfect simple random sample is that the population is exactly normal, and we know the population standard deviation, like I just mentioned, that's like unrealistic. But it's a good place to get started. So let's go over an example, right? So the reasoning of statistical estimation. So a report gives data for 936 men aged 20 to 29 years, and the mean BMI or body mass index of these 936 men is 27.2. So that's our sample statistic. On the basis of this sample, we want to estimate the BMI of the population of all 23.2 million men in this age group. And in order to match the simple conditions that we gave in the previous slide, we're going to treat this simple random sample from a normal distribution with known standard deviation of 11.6. So in order to estimate the unknown population mean mu, we're going to use our sample mean. And we don't expect our sample mean to be exactly equal to mu, so we need to say how accurate this estimate is, okay? So, because we're taking a sample, the average BMI of young men is going to have the standard deviation sigma over the square root of n, right? Because we're taking a sample, the standard deviation is going to be different than that of the population. We divide it by the square root of our sample size. And we get 0.4 if we round it. The 95 part of the 68-95-99.7 rule for normal distribution says that x bar is within 2 standard deviations of its mean. In this case, because our standard deviation is 0.4, we multiply that by 2 to get 0.8. So in 95% of samples, our sample mean will be within 2 standard distributions of the true population mean. So we can construct a confidence interval. So if I take the mean, we have our sample mean, we'll put it up here, of, our sample mean was 27.2. That's our X bar. And if I go 2 standard deviations below and 2 standard deviations above, that's my cat. She's fine. She's just wanting attention. I should have 95% of my data. So I'm going to take my sample mean minus 0.08, which is 2 standard deviations below the mean, and add 0.8 to put it 2 standard deviations above the mean, and estimate that our true sample mean lies within the interval and will be correct 95% of the time, because it's a 95% confidence interval. So adding and subtracting 0.8, I don't know why they said 0.6, 0.8 from our sample mean of 27.2, we're going to get this confidence interval. So for this, we say we're 95% confident that the mean BMI, mu, of all young men is some value in that interval. So no lower than 26.4, but no higher than 28.